the last day we have discussed some basics about machine learning. Okay, there we have seen that we are talking about some experience, and based on the experience, whatever we are learning, we are based on our learning, we are predicting some target. Okay, so we have seen there are huge names at the end of the slide. We have seen that there are huge names of machine learning algorithms. But whatever be the algorithm, the main purpose is you need to find one mapping. That mapping may be some function f, and that function, that mapping should come from your experience, from your training data, and in the testing phase, you will give some input, test input x, and you will correctly predict some target related to your test input x. Okay. So based on your application, based on your requirement, based on the limitations of previous, algorithms limitations, we are basically each and every day nowadays, as it was told, that around hundreds of machine learning algorithms are coming each and every year. So this field is evolving. Now today we are going to talk about deep learning. Why we are focusing here, we will in detail talk about the structure of this deep learning architecture, and we talked about a few known recent architectures, because in our embedded machine learning discussion we will see that these type of architectures, basically we will apply some kind of optimizations, some modifications on these architectures. And in embedded scenario nowadays, if you see the applications, that may be some prediction, that is image based prediction. In some examples that we have taken in case of Alexa, okay Google scenario, there are some audio, some speech processing related predictions. So this image, speech processing, audio processing based predictions, they are better handled by this type of deep network or deep neural network. In turn, we will see. So that's why here we will see much detail. What are the components present in this DNN or deep neural network? What are their importance, and how are they organized, and how, most importantly, at the end of this today's discussion, maybe we will discuss few architectures. Like maybe for the few of them you heard the name, like starting from LeNet, then Google Net. So these type of architectures, how they are different, where we will see the basic components are very same or very similar, but sometimes only how you are placing those components, how you are organizing the components, what the size of those components, based on that this architectures differ and they evolve. Okay. So this part maybe we have discussed that we know that machine learning, it is a field of study that gives computers the ability to learn without being explicitly programmed. Within the machine learning whole domain, there is a one subset we will talk about here, that is brain inspired. That means here we will take the algorithm that takes its basic functionality from biological concepts, like how our brain operates, the neuron, synapses, similar terms we will see here. And based on those concepts, basically these subset of machine learning, this part has been, conceptualized. So first, take this way, very quickly, that how does brain work? Maybe your 9-10 biology concept. You know that the basic computational unit in our brain is neuron. And this neurons, they are connected through some units that is called synapses. They're connecting layers. These neurons, you can see here in this diagram, they are connected one to another They receive some input from one and they pass that input to the next component. And how, one second, I should have, how this one neuron or some signal coming from one neuron to the other, how they will actually influence your activities, those are basically not always same. Mainly some influence give some output, some other input, based on some other input, you act differently. So that means here comes the concept of some control or some control variable related to those signals. Exactly in this way, with this neuron and this synaptic weights, with this concept, this machine learning domain, this subdomain, and we will come back to this spiking domain, has been conceptualized. So here when we talk about DNN or deep neural network, we think about something this type of architecture, where we have some input layers, we have some intermediate layers, we call them a hidden layer, and the output layer. You can see these components, you can just, this point, you can name them or term them as neurons, and their connections, those are synapses. Of course, as we talked about from our biological sense, we know that these synapses, they will be associated with some weights. Maybe we have some next slide, we can go here. So we have input layer, output layer, synapse connected with it, and these synapses, they are associated with some weights. So basically, in our computation unit, what is going on? We are receiving inputs from different input ends, or you can think about different nodes from the input layers. We have the synapses associated with some weights. So effectively, the input coming from that input node of that input layer, it is basically contributing as this W0 X0 dot product of this two values, W0 X0, W1 X1, W2 X2, etc. And this cell body is doing the summation, the accumulation of that. Okay. So after this, there another operation, you can see this one, this function, that is the activation function. Now we will see step by step more detail what we mean by activation function, why it is necessary, in which context, how it is necessary in training and testing part. So just first of all, you think that this is when we think about neural architecture, neural network architecture, basically we can think some input layers, some output layers, and intermediate, some hidden layers. Now these hidden layers may be a single layer, maybe more than one layer. Okay. And so when we talk about deep learning, basically we can think this way. There are concepts of layers, layer-based learning. Okay. So here, first try to think through this basic example. Let's say you are trying to train your system about the image of a particular car. Not a particular car. When you are training your system, you are taking huge data sets and they are having information about multiple car images. Now, when it is learning the image, you can think that the image is getting represented as image pixels. Okay. So maybe this is a matrix of multiple image pixels. Now, from that image matrix, image pixel matrix, first you have to extract some broad level features. In this learning term, we can term them very low level features. Here you can see from this image, you can extract maybe some curved lines, some slanting, left slanting lines, some right slanting line, some circles. So these are different types of features you are extracting. Now once that is done, this may be in this your second layer. So this second layer is giving you very broad features. You are somehow extracting. We will discuss how we can extract, etc. But somehow we think you can extract these features from isolate, maybe they isolate these features from your input image. Once this is done, again you have to go deeper of these low level features. You have to, now you have, maybe you have got two different left slanting lines. Now you have to isolate, you have to search for more deeper features within those slanting lines. And based on that, you will get some better visibility, some better understanding of that given image. This way, layer by layer, you proceed and you will basically extract first from high level, very low level feature to some very accurate features. Okay, and that way you can identify, okay, this is particular the car from a particular company. Basically, you can understand this way when you are inputting multiple images of cars. Maybe they are from different makes, different manufacturers. Initially, just from the low level feature, from the first layer or the second layer, this curvature, this the area of wheels, etc., these features are almost same for different cars. From these features, from very low level features, you cannot isolate that whether it is a particular type A car or a particular type B car. For that, you have to go deeper, and that we go layer by layer. So here the representation of your input or representation of your test input or maybe training input, you are realizing layer by layer and you are proceeding. And as you are going deep, you are getting the idea of more intense features. And that's why this part of learning we term as deep learning. Okay, and this is inspired by the biological our brain. How our brain is working based on that concept. Now we should go back just for a few slides that we skipped. Now, when we are talking about this brain inspired, basically there are another type of machine learning algorithm that is called spiking networks. Now, this spiking network, it is, it is also holds the concept of this neuron, synapse, etc. But there is a basic difference with the traditional neural network that we are working with. In the spiking network, this neuron reaches a certain potential and it spikes and it resets. So this reaching up to a potential and it is resetting the potential. This is the main feature of the spiking architecture. But we are not discussing much because in our case we will talk about more. We will focus on this part, this neural net component, where we will talk about CNN. We will talk about recurrent network. So what are the difference? What are the basic architecture? All these things. Okay. So, okay. Now come here. We were here, I think. So now you understand that when I am inserting the first, image pixel details from this card, that is forming my input layer. Okay. And at the last stage, when this is some fully, we will talk about later what we mean by fully connected layer. But in this last layer, you can see all the connection, all the nodes are connected. After that, when we are getting the final, maybe classification result, that, okay, this is this type of, here it is something written, some Volvo XC90 or something like that. This is the type of the car. We are classifying that. So after reaching there, so that forms my output layer. And all these in between layers, these are hidden layers. Okay, hidden layers. Now, as we mentioned, like our brain, when some feature is contributing to, to develop some data flow from this input node to output layer, of course, it is associated with some weight. Weight means how much it is controlling. What is the how much intense or how much lesser the effect of this input feature when we are forming some output feature. Okay, so based on that we have some weight associated with it. Now comes the activation function. So far, whenever you are getting this W1, X1, W2, X2, etc., all these inputs, the initial part is called accumulation or maybe general summation. After that, when we have got all the effects of all the input features, and there we should say the effects of all weighted input features. Once that is done, now we have to develop some condition or some function that will tell me what I want. With this, whatever knowledge, again the concept of experience, whatever experience I have gained from this input features, from these weighted input features, what I want. Do I want that with this input features, how my output feature will look like? Or do I want some probability? Whether based on these input features, some probability I want to denote that I want to get that whether this curve will belong to, what is the probability of this curve that it will belong to some class A or some class B. Or number 3, whether this card is belonging to a particular class. Yes, no, these type of results. So what I want, what type of output I want, what is the basic purpose, basic target of my output layer. Based on that, we develop this activation layer. We will see in detail how this types of activation layers look like. That is the purpose, that how my output, how shall I develop that output layer. And also we will talk about some non-linearity step by step, that this activation layer function, how it gives non-linearity to the structure, etc., and what does it mean by this non-linearity. Okay. Then before that, this you can see that you have multiple synapses, and they may use same weight value. And there are these are the input pixels. This is the layer 1, and this is the connecting this neuron output to the next layer. Yes. Now this is it. This term we will heavily use, that is fully connected and sparsely connected. Not only for general terminology, this is why I'm telling this term we will mention again in our embedded scenario. When we talk about fully connected means, you can see these nodes coming from this input layer and going to this hidden layer. They are densely connected. That means all node is having some connection to the other nodes in the next layer. But here, if you can see that some nodes are connected, like this node is, there is no connection between this and maybe this. You can see H1 and you can see O2. If you see, there is no connection between these two nodes. That means based on your features, it may happen that these nodes are somehow connected or some nodes are not at all connected. Okay. So based on that, we can see there are two types of DNN architectures. One is fully connected and one is sparsely connected. Later on, we directly refer to this fully connected architecture. Then you should understand our fully connected layer. You should understand in this layer, all the nodes are connected to the next level nodes. Okay. Now, this is the feed forward. Of course, this is quite straightforward to understand from the name. Feed forward means from this input layer or the sending layer, there is only path from the nodes from this input layer to the hidden layer. That is a feed forward network. Whereas if you see here in this output layer, that some path is forming the feedback. So that means there are some feedback path present in this output layer, and it may happen that in some DNN architecture this feedback path is present, and in some DNN architecture this feedback path is totally absent. Now we will see what are the advantages and disadvantages of these type of presence or absence of this feedback path, and based on that there are different types of popular DNNs. Maybe those names you have heard. First one is fully connected. So far you understood what we mean by fully connected, how it looks like. Next we have CNN. CNN may include, you can see like this, CNN may include some feed forward paths or some sparse paths too. Next, with some feedback, we will talk about recurrent neural network. Basically, we will talk one by one in detail. And then we will talk about some feedback along with some storage. Specifically, this language processing on these type of this CNN, mostly I should say that this CNN, these are mostly effective when we are talking about this image processing. But this long short LSTM or long short term memory, these will be useful when we will talk about some kind of audio processing or some kind of language processing. So those cases, this LSTM will be useful. Okay. So these are the basic components, basic structures of DNN. So do you have any questions so far? You can stop me and ask. Okay. Anyone?
In the previous slide, referring to that one.
Here,
Yes,
this
ma'am.
one?
Yes, ma'am. The
Yes.
feedback will be returning back to the means the previous layer or to that layer only.
Feedback here, this is showing that it's returning to this output layer only. Okay. We will see different when we discuss about this required RNN in more detail. I think on this feedback your questions will be clear. Okay. So for this the example shown, it is coming to this only to the output layer. But there are different types of feedbacks we will discuss. Okay. Anything else? Okay. So again, maybe someone was asking last day that whether this deep neural network can it be supervised or unsupervised. Basically, these type of architectures can be supervised when you have some training sets as inputs, outputs, and they are leveled. I think this part we have already discussed last day. Some are unlabeled, and mostly this type of independent component analysis. That way we handle unsupervised learning. Semi-supervised, you can understand, both are partial. And this reinforcement, I think maybe we have also mentioned this one, that reinforcement where it is based on some reward and punishment exchange between some agent and environment. So all the possibilities are also possible here. Now let's come to this part in detail. As we mentioned that when we have one image, we are passing that to some convolution layer, when we are talking about this deep convolution neural network, DNN. And then it is extracting some low level features, maybe the same thing we discussed with the previous example. Then we are passing through multiple this type of convolution layers, and then we are passing that, getting some high level features, and with that high level features, you are actually classifying that, and you are actually identifying the actual class of your input. Like when you are giving this car images, maybe one car, maybe normal Innova, one is Innova Krista. So for to identify in those minute details, you need to have the knowledge of this high level features. Okay. So, okay, before that, tell me one thing. Maybe this is nothing related to neural network. What do you understand by this convolution? Anyone? The word convolution, what does it mean to you?
Now, applying a filter repeatedly over something.
Yes, filter is related to neural network. In general, more you have used in mathematics also. You have used convolution function, right? You have seen in mathematical libraries, and you are from electrical electronics background. So when you do this convolution function, what do you do practically? Let's say you are like you are doing f convolve j v something, some two functions you are convolving. When you are doing, what do you want to observe with this convolution function?
Is this a multiplication?
Of course, it will be implemented by multiplication, correct. And someone told about applying filters, that is also correct. That is what we are doing. But I am asking about the concept. Why we are naming? Yes.
And is it? It is element-wise multiplication, like
Yes, correct. You are
AI.
correct. Multiplication, see, addition, multiplication. When we are telling those are just operators. Okay. I'm telling what is the significance, what we want to do when we, in mathematics, when we just apply one function to another, and when we write convolve, you can see in MATLAB or etc. also, you can check it. That what we want to observe.
Repeatedly.
Pardon?
Filter repeatedly.
Can you come up once again? I can't hear it. Hello? Okay. Maybe some sound problem.
Is it like how filter modifies the image to get features?
Yes, correct. Maybe some of you already heard about this neural network. You know some basics. Correct. Whenever in convolution layer, what we do, we just feature related filters we take, and we do some convolution. Convolution means nothing but some matrix multiplication operation. That is the next slide I was about to tell. Correct. But from mathematical point, why we suddenly thought this name as convolution? Why not something else? We could have named it as feature multiplication, right? The reason is that when you go and check in MATLAB, when we do this convolution function in mathematics also, you are applying one function to another. Basically, the idea is we want to check how the shape of one function is actually changing with the effect of another function. Basically, this is the concept coming from mathematics, that how we can extract some shape with this convolution when we are applying some function to another. We can how the shape is getting changed, or whether we can extract some particular pattern from the previous function or not. So in mathematics also, when we analyze with convolution function, that is the whole purpose. Here also now you think, those who knows, otherwise for others I will again discuss. In this convolution function, what we do, let's say you think in this way, you have some input matrix that is coming from your that input image pixels that is forming the matrix. On top of that, you are applying some filters, not on the whole matrix together. We will talk about stride, etc. later. But thing is that you are applying this filter. Filter means nothing but, again, some, you can think about another matrix, and you are doing this convolution function. You are doing this matrix multiplication. And with this multiplication, whatever result you are getting, basically you are trying to extract if there in some special, I mean, that is called in particular locality of that image, do you have that particular pattern? So that's why we term this layer as convolution layer. In maths also, when we apply one function to another and we just try apply this convolution function, we try to extract what can be the shape change or what can be the pattern extracted based on the, I mean, if some particular pattern can be extracted from the function or not. So same concept comes here. We just try to extract some pattern from this input matrix. That's why we choose filter. You understand that for that we have some filter, I mean, this RS values that we define this filter matrix, okay? And then we are applying this matrix multiplication on this whole large matrix, okay? So that's why we term this layer as convolution layer, and that we do repeatedly. It is not that we are telling this convolution, naming this as convolution layer because we are doing something repeatedly. No, we are naming that because we are using it for some feature extraction, pattern extraction, and we are repeatedly way from high level, low level. We are going to some high level features. That's why we have so many layers, multiple layers, and making my architecture deeper and deeper. So initial concept you may have, the more layers we can add, if we the more layers we will add, the more number of features, the more deeper, the more high level features we can extract, and that will be good for my this architecture. But at the end we will see that is also there is some limitation of this concept also. Once we increase with this layer, there are some associated problems. But come back to this as of now. So this is the we were talking about that features are the elements of your input vectors. The number of features is equal to the number of nodes in the input layer of the network. That means when we thought about this type of input layer, these are the number of layer, I mean the number of nodes present. They are basically the number of features. Okay. Next, let's say here one example is given that you are trying to classify where from your data set that whether one input is a man or woman. So for that, you are basically considering the input features at the height, weight, and other the hair length, etc., etc. So those are the features you are considering in your input layer. And the more the number of features, more the number of nodes in your input layer. Okay. Next, okay, fine. You have developed your input layer. Now, as we told, you have to extract features. And for the extraction of features, as the name suggests, you have this convolution layer. Convolution means all of you already told, you already know that you have some filters. Filter means nothing but some matrix. Again, you are doing some matrix multiplication. And see, this is the filter. This filter size remains, I mean, smaller than your input feature map. Why? You have to check, like, you have to check that particular pattern on multiple locations of your input feature map. Okay. So, and then you form this output feature map, but of course that is not in one step. We will have some multiple intermediate steps. We will discuss them one by one. Okay. Now, you have this filter, this is called the sliding window process. That means you are considering this full image matrix, and then you are applying this filter here. That means you have taken maybe some 3 cross 3 submatrix, and on top of that you have applied your filter. Once done, you are shifting, you are sliding that filter, and you are again doing for checking for this next 3 cross 3 submatrix. You are again multiplying your filter values with this next 3 cross 3 submatrix. This way you are sliding and covering this whole input matrix. That way, whenever you are covering the whole matrix, basically you have in each and every location repeatedly you have checked for some particular feature, for maybe that feature may be some particular shape, particular boundary, maybe some curved line, maybe some straight line, maybe some circle, whatever it may be. Based on that, you have developed your filters, and that filters you have multiplied, you got some output matrix. And that is basically forming your output feature map. Now, when we are talking about this word feature map in general, it is the whenever you have applied some filter to some matrix, to some input, and the output generally termed as the feature map. Okay, you will see these terms repeatedly: input feature map, output feature map. So it is, you can consider that whenever you have applied some filter on the input matrix, you have got output, and that output you can term as related feature map. Okay. Now here, so far what we have talked about, we have talked like this. You have just considered one channel. Okay. Now, for example, why this channel concept is important? Okay, you have represented the message pixels, that is fine. Now, this message pixels, when you are dividing into channels, let's say this may be meaningful when you are dealing with colored images. Yes? Any questions? Okay. When you are dealing with colored images, maybe for colored images, you can think about RGB 3 channels. And for these 3 channels, you are doing the same operation. You have considered one input feature map, you have taken one input matrix, from there you have applied some filters, you have considered the input feature maps, and generally you have proceeded layer by layer, and finally you have accumulated the whatever you got, and then you are forming this output feature map. So not only this height and width of this matrix, you are also having this channel information related to your color. Basically, you can think this way: whenever you have this colored image, you are again tearing up your inputs, and you are passing them through multiple channels. And in those multiple channels, you are applying filters, and you are doing the same repetitive operations. Okay. So there may be many filters again for many channels, and that way, whenever you are tearing up your input into multiple channels, you may have many output channels. In some cases, or in some other cases, you may have to accumulate all the outputs coming from multiple channels, and then you have to form the output feature map. So both are possible based on the requirement of your application. Okay. So this is shown that many input feature maps, channels, etc. So these are the, okay, we will come back here as and when required. These are the variable names what we are going to use in our coming slides. So now the question is, now I think you can understand, whenever we are basically generating the output feature map, what we are doing the same thing, whatever we discussed before. We are multiplying with some weights, okay, some input values, okay. But this time the complexity is that if you go back, this indices, you have to, it is like maybe all of you have done this matrix multiplication, right? So similar to that, this is also a matrix multiplication, but here you have to consider the number of channels as an input. You have to consider height and width of your input matrix, input feature maps. You have to consider the height and width and the number of channels associated with your filters. And for them, like in general case, you used to, for matrix multiplication, you used to do this type of operations. Aij, comma maybe AJK, sorry, BJK. So you can think that all these input pixels and the filter inputs, filter values, based on row and column fashion, for each channel, you have stored some in some array. So for input matrix also, you have stored the values in some array. For filter also, you have stored those values in some array. And based on when you are doing the multiplication, basically you can see here, you can just accessing based on the indices, you are just accessing those weight values. The weight values basically coming from your filter values, filter inputs, arranged in a row column fashion. For particular channel, you are fetching that filter value. You are fetching the value from your input feature map and you are doing multiplication, nothing else. And while doing so, again, you have to take care of one extra parameter, that is U. You can see here, U is the convolution stride. That means you are considering the same input matrix. You are considering the same filter. But also you need to consider where your filter is placed, or for which stride. I mentioned the stride, that when you are shifting that value, how much shift you are giving, how much slide you are giving to your filter to cover the whole input space. So that stride value, stride feature is also important, and you have to take care of that also when you are actually fetching the input feature map. So once you are getting the particular input feature map, and when you are getting the particular filter weight, you are basically multiplying, and then you are adding some bias to it, and that way you are getting the output feature map. Okay, I think this part is quite straightforward. Only that you are representing or you are storing them in some array format, and that way you are forming the tensor. We will talk about tensor, what we mean by that later, but we are we are representing our input feature map, we are representing our filter, and that way we are doing this multiplication required for this convolution layer. Now you can understand that for one layer, maybe how many, for one layer, when you are applying stride, and for one, first of all, when you are considering one filter to input value multiplication, that is one matrix multiplication, and that will be governed by the size and the height and the width of the filter you are considering. On top of that, number 2, you have to consider number of channels with which you are working on. Number 3, you have to consider the stride value. How much shift you are giving to your filter, and based on that, how many number of operations. Basically, you can understand that if we are, this is my first multiplication with my filter, then maybe I have considered a huge stride, maybe a large stride, and I skipped multiplying considering anything in my next multiplication, and again I have considered my next filter position here. That means I have not considered any overlapping. If that is the case, of course, the number of computations will be lesser, but that will affect on my training accuracy or testing accuracy. So that means whenever I am trying to reduce this computation, this accuracy will change. This part we will again discuss in detail. Now think in some embedded scenario, okay? Or you think of when we will talk about embedded scenario, in some cases, maybe you need some real-time prediction. If that is the case, you have to, for that prediction also, you understand that you have to do these huge number of multiplications, then only you can actually correctly predict your target. Okay. Now, to optimize your problem, you have to improve your performance. You are trying to find some optimization way out. One optimization way out may be that you may, the shift you may consider here some high shift. That means you are skipping some intermediate computation, intermediate multiplication. Of course, that will improve some performance because you're skipping skipping some number of matrix multiplication, and cost of matrix multiplication is huge. That means you are saving in terms of some computation time. But that in that way also you have to check the accuracy you are getting while you are skipping some amount of operations. The accuracy you are getting, whether it is acceptable for your application or not. So in our coming discussions, whatever solution we will propose step by step, we will each time see if in some cases that the accuracy we are getting, that will be acceptable. In some cases or some applications, we cannot adopt that type of solution. Okay, so we will have that discussion repeatedly. So this stride related discussion will be one. Okay. Next, so now I think you understood that to implement this one, we have to do this type of huge multiplication, and that is also only for each output fmap value. Now the number of features increase in your output node, output layer. The number of features increase in your input layer. Of course, you can understand based on that your accuracy will gain, but your computation will also be, that will be also some problematic. And there will be a trade-off, and that trade-off we have to decide how far we can go. Now, maybe this slide we already mentioned, shown the last day, that when we are talking about this Amazon Alexa, like you're there also, we have to run some voice related prediction. Maybe whatever instruction you are giving, that instruction may be need to be predicted correctly, and and based on that the classification will be done, and then only Alexa can complete your instruction. Okay, but to do that, Alexa needs some huge these type of computations, and it is only having the support of this such low RAM and some other low or constrained processing features. Also the support of low power, maximum power it can be reached up to 9 watt. Now, this is the case for all embedded devices. Embedded device means maybe for some of you, this word is not so common. When we talk about some embedded device means we consider one system, some processing unit, maybe this is your embedded system, that is a part of a bigger system. Okay. Or this embedded system, the main feature of this main requirement to develop any embedded system is that, first of all, it should be of low power. It should be of with some restricted RAM, restricted memory, restricted resources, and most of the time, the output it should give, it is fixed. That means it is deadline restricted. Deadline restricted. And here is our challenge. Anyway, next year we will talk more about this embedded system. Let's focus on this machine learning part now, as of now. Then this part also I showed you last day. Have you tried, any of you, to go through these examples?
Yes, Professor, I have.
Maybe you will not understand all the modules, but you can get a feel that how this classification and those things are going on. Now, come back here. So when so far maybe you have understood this. What is the basic idea? What we have inside this convolution layer? We have some huge number of multiplication. We need some huge number of multiplications. We have the concept of filter. Basically, we need to do some huge matrix multiplication. Now, this convolution layer, why we considered it first? Because this is the basic of feature extraction and pattern recognition, and also this is takes the from our embedded perspective. This takes the 90%. For this convolution for the presence of this convolution layer, it is the generating the 90% computation overhead. That means it is the most costly part. Whatever we are going to discuss, not only this convolution layer, we have some more layers. We will discuss one by one. But this convolution layer is the costliest part. So whatever optimizations later on we will see, that mostly we will focus in this part. We will try to optimize this convolution layer, or in terms of some weights, in terms of computation operators like the multiplier. You tell we are basically doing multiplication. So how we can approximate this multiplication and we do some computation over it. So these things we will see. We will focus on this convolution layer more. Other than that, we have some pooling layer and normalization layer. So it is already in that what I told, that convolutions account for more than 90% of the overall computation, dominating the runtime and energy computation. So this is the most bulky layer, and we have to optimize this one for our embedded requirement. Now come to the next part. This is called pooling. Okay. Now you remember what we discussed, that we multiplied with that filter and we got some output. Okay. Now on top of that, we are applying some pooling algorithm. First of all, let's see what we are doing, and then we will explain why it is important. The pooling, there are two types of pooling. Maybe most of you heard, that is max pooling and average pooling. What we do, whatever in max pooling, whatever once we are considering to pool among this 2 by 2 location, we just take the maximum value, like 23, 7, 10, 1 we have. We will just directly take the 23. From this, we will take the maximum value 9, 5 and 12. So that way we are forming the pooling output. Similarly, when we are doing this average pooling, we are taking the average of these values present in this matrix, and the average value will be considered. Now the question is, this is the way what we are doing. This is the operation. First, straightforward one advantage, maybe one thing you can observe, that can you tell me what will be the advantage when we are doing this pooling? Just looking at this slide, what do you think?
Ma'am, the dimensionality will reduce for the complex.
Exactly. So this is straightforward. That when we are actually multiplying in that case, there is we are working on a huge dimension. Here, the pooling, the first thing is that you can observe that it is helping you to reduce the dimensionality. But on top of that, what do you actually do? I mean, what is the main purpose of doing pooling? It is that when you can see one term, it is written here, that is called translation invariance. Okay, that means when you are applying here, if you go back, you are applying this filter on this image, you are actually following the locality reference what you have in your input feature map. Like whatever you have values you have in this locality, you are just doing multiplication with this filter. So the training, whatever you are doing, that may be very much affected by the locality of a particular pattern. What I mean in a simpler way, once you have actually trained your system with a dog's image, an image was that time was like this, some vertical image of dog. Okay, and you have continued to apply these filters in this way and completed your training. But when you received your test data, maybe that time the image was slightly tilted, similar dog image, but it was slightly tilted, some rotated, or some part is cropped. Now this part, there is some translation, and this translation, if you do not train your system, then this translation cannot be actually during the testing phase, your system cannot predict that correctly, cannot identify that okay, it is a dog's image, but okay, slightly tilted. So this type of translation, to identifying those, this pooling layer is very much effective. Pooling layer, you can think about some representation. These average values or these max values, they are also representing the whatever input values you have considered from your input feature map. But there are some on top of that, you have done this max or average operator application, so that it can there is some proof that it can become this type of translation invariance, so that this type of cropping, shifting, these type of translation can be better handled, and that is another purpose of applying pooling layer. And of course, one direct advantage of pooling layer is that that is reducing the dimensionality. That is quite straightforward. Okay. So again, to implement this pooling layer, you can see what you need. This one for the again some traversal of these array values or these matrix values, and then checking this some max comparison, or once you are talking about this average pooling, maybe some here this part will be replaced by some average computation. That is basically some addition and some division. So this will be the operation. But this max computation, this average computation, they are also in numbers. If you think that you are applying in smaller blocks, so there will be huge number of this max computation, this average computation, but still it is not as costly as the multiplications, the filter based multiplications that we have considered in our that one convolution layer. So that way, pooling layer or this pool layer, this layer also contributes to this computation requirement, huge timing requirement, huge resource requirement, but that is not also as huge as the matrix multiplication required in convolution layer. That's why when we talk about, when we are thinking more about this, how to optimize this type of CNN network, we mostly focus on that CNN, that conv layer of this CNN. Okay. Next comes the normalization. Okay. Now this is another normalization step. What we do, we basically map the training data set to some trend. Okay, to some trend. We map them to some trend where we consider the mean as 0 and the standard deviation as 1. Okay. So whenever we are doing this normalization, there are some experimental results and some not so formal proof, but some proof that show that it is believed to be that it is a way to get some high accuracy. It is a better. That's why we actually apply this normalization in the input layer first. But then you can think this way. You can go back to your structure. When you have this type of input layer, you are applying some normalization. Okay. Then when this you have done some computation on this hidden layer, then also this distribution may get disturbed. That's why again you have to apply some kind of normalization after this hidden layer, and this time it is called the batch normalization because you have to apply in all the synapses on all the values, and you have to apply these batch normalization to get your data mapped to some trend with this particular mean and this standard deviation value. Okay. So this is the mathematical expression how you are actually we have mentioned why this normalization is important, but this is the expression how you are modifying. This is your input data with the data mean and this standard deviation, how you are modifying your input data and mapping that to some other value y, and then in the next level you are considering that input normalized input for your next level processing. Okay. So now I think this part is clear that what you are doing in this convolution layer, and associated with that, why do we have pooling layer and why do we have this normalization layer. Now comes one of the most important part, that is the activation function. Maybe as of now you know that whenever we have this type of weight, we are multiplying that with input, we have the bias, and on top of that we are adding some function and we are terming that as activation function. Now why this activation function are required? We will come to this fully connected layer later. First, just we will mention what type of activation functions do you have, and then we will see that why we are actually considering this activation function. Now this is the sigmoid function. Just observe the pattern of that these functions. You can see it can output 0 or this way or this way based on its value. It may go up to 1 value. Okay. Now in this tangent value, this is this F shape of sigmoid that is quite similar to this tangent value. Only the range is from -1 to +1. Okay. So now if you want you have some application where you will check whether the output, maybe a direct classification, output will be 0 or 1. Then you can apply there this type of sigmoid function at the activation layer. Once you have actually accumulated Maybe now I hope you remember where we are applying this activation layer. Once we have accumulated all the wi xi terms, we have done summation on them, and on top of that we are applying this activation layer, and based on this 1 or 0, this type of output of the function, we are classifying, or we are making some decision about the target. Similarly, these two are quite similar, and their problems are also very similar. We will talk about that vanishing gradient problem comes due to this shape of this sigmoid. Okay. Another type of activation function is, this is called the rectified linear unit, or in short we term them as ReLU. Maybe this is the mostly used, this ReLU and its variants are mostly used nowadays. It's a very common activation function. First, look at the structure, and then we will talk about why in some cases, we avoid this type of sigmoid function, and why this ReLU is gaining importance. Okay. Now, this is the structure. So, what does ReLU output? If there is a negative number, ReLU output 0, or if it is otherwise, it outputs the maximum value between 0 and x. Okay. So that way, one second. So these are the options. Maybe those of you already use this type of activation functions in some projects. Maybe from these options you have used either sigmoid or tanh or some versions of it. Now we will see what does it actually mean. I mean, why do we need this? Cool. Once do you have any questions so far? You can ask me. I just need to change the slide.
Ma'am, I had a question.
Yes.
Ma'am, suppose if we train a particular convolutional neural network by showing it one particular picture, or rather many pictures, and then we let it identify or test on another picture, and that picture, what we do is, instead of orienting that picture, we change that orientation of the picture. Suppose we rotate it by 30 degrees or something. So will it be able to determine or classify that picture with the same accuracy?
So that's for that what we discuss about this pooling layer. Okay. So whenever you have pooling layer, you can okay, I will open that slide once again for you, but let me explain first. So pooling means it is from a smaller locality or smaller matrix. It is not taking the exact values. Just not exact values what you are getting by multiplying the filter and the input feature maps. It is taking some representation of it. Okay. So there are different types of the pooling, those type of techniques, and those are actually used for this translation invariance property. This rotating, shifting, cropping, whatever you are telling. If in your training steps, okay, there are two steps, training, and based on that we will talk about some part about backward propagation. So there we will see, based on that we update these weights. So if you have included these properties during your training steps, of course it can learn, it can predict correctly in spite of your input is tilted or rotated or something like that.
Oh, but for rotation, that means we can apply a different kind of pooling. maybe.
Exactly. Some pulling, if you incorporated that effect in your pulling part, then only that will be handled in a proper way. Okay. Otherwise, not.
Yeah.
Yes.
Thank you.
Wait a second. Downloading. One second. Okay. Maybe there's some. Okay. Okay, you can see the slides, right? Hello? Can
No, ma'am.
no? Now?
No, ma'am.
Oh, still no. Oh, okay. Is it visible now?
No, ma'am.
Oh. Is the screen visible? The shading is visible?
No, ma'am. Nothing is
No,
visible.
nothing is visible. Now is it visible?
No, ma'am.
Log out, login. Still no. Still not visible.
No, ma'am. No, ma'am. Not visible.
Oh. Is it visible now?
Yes, ma'am.
Visible. Good. Don't know what is. Sorry. Okay. So now you have the idea that these are the options for me. Now the question is why it is important to have so many activation functions and what is the purpose of it? First of all, the choice of activation function in the hidden layer will control how well the network model learns the training set. Okay. The choice of activation function in the output layer will define the type of predictions. As I told, based on your application, what you want to do, what type of, how we want to classify or how we want to get some probability about your target. So what you want to do, what output you want from your model. Based on that, the activation functions you will use in your model. Okay. So sometimes this activation function is called this transfer function. That it is basically output features is input features. It is outputting to that. It is mapping to that output. So that's why it is the transfer function. Okay. So if the output range of the activation function is limited, then it may be called a squashing function. Maybe the squashing term, those who have worked in machine learning projects, you have heard a lot. Now, what do we mean by this squashing? Now come back again to your sigmoid. Okay. So whenever this output, you are ranging between 0, 1. So you have given some input range, you have added some weight, maybe some large values of weight, then some accumulation, doesn't matter. After that, when you are applying this activating function, basically you are squashing the value within this 0 to 1, or for this tangent where you are ranging, you are actually squashing the value within this particular range. And that's why these are called particular types of activation functions. They are called squashing functions. Okay. And non-linearity also given, and the activation function is used within or after the internal processing of each node in the network. Of course, that we have also seen that when we have like this one, when you have low level features, then your convolution layer, you have done the convolution. That's the convolution means you have done this this filter related multiplication etc., the feature extraction etc. Then you have done pooling for handling that type of added requirements like rotation, like shifting etc. And then that way you have done some dimensional reduction also. And after that you are actually applying this activation function. So you can see in both the diagrams, for this convolution and for this fully connected layer, in both cases, after doing this internal functionality of this node of this layer, then only you are applying the activation function. That means activation function is finally chopping the unnecessary parts and exactly focusing which information you want to deliver in the target part or the output part. Okay, the activation function is used within or after that we have already told internal processing of each node in a network. Although networks are designed to use the same activation function for node in a layer. So that means for a particular layer, the general concept is that we are using the same activation function, because in general the purpose of using the activation function is same for all the nodes. Okay, basically node means, if you remember, we already discussed, that is mapping the features. Okay, and then the all hidden layers typically so that is obvious that we told that for all layers we are using the same activation functions, and the output layer will typically use a different activation function from a hidden layer, and it is dependent upon the type of prediction required by the model. Okay. Okay, this part we will talk a bit later, because why this we are why we are talking about this differentiable requirement or derivative calculation of this activation function. And when we talk about back propagation, and for hidden layers, it is in general we use this ReLU, as we told that this is a okay. For these two slides, you can skip as of now. We will discuss in detail the back propagation part. I think then you yourself can understand why we are choosing ReLU over sigmoid in that case. Okay. So these are the options for output activation functions. In general, linear output activation functions where this is something just adding some extra bias kind of thing, nothing else. The sigmoid we already mentioned, and the softmax we will talk it later. Next, it comes the fully connected layer. You can see this is in general. Whatever we will discuss more, with step by step we'll discuss about some recent particular architectures. And there in everywhere you can see this fully connected layer comes at the end. You can see here also, maybe whatever example we have taken, you see these examples when it was shown, the last layer it was taken this fully connected layer. When we are talking about fully connected layer, then the activation is we are thinking that it is fused with that layer. That means this activation is a part of this fully connected layer. Together we are calling it fully connected layer. But always, whenever we consider this CNN or convolution neural network, you can see in general, at the end we consider the fully connected layer. Because if you remember the basic structure when we first discussed this fully connected layer, all the nodes are connected to the next level node. So that means at the final level, whatever experience, whatever learning we have gathered based on multiple features, we don't want to miss any of them. So we want to accumulate the effect of all those features. That's why always in general in the last layer we do not allow any kind of sparsity. There also the same, the concept is same, that we have that input feature maps, we have the filters, and we do the convolution, and when we go to that fully connected layer, we consider the connection between all the nodes. That is, in general, you will see, we will discuss LeanNet, AlexNet, all this, a few recent architectures. There also you will see the same thing. That means we want to maximize the inputs from whatever experiences we have gathered so far. So that's why the last layer, there is no sparsity considered. So now quickly talk a bit about the CNN literature. Now maybe I think you have some idea how this CNN structure or this deep neural network structure looks like, what components we have, and what's their purpose. Now we will see that the first, for the LeanNet, that was the first CNN architecture. That was, that also started with these basic components. And next, coming to AlexNet, we will talk about this GoogleNet. All they are basically considering some rearrangement of these filters, of these convolutions with certain purpose. Okay. So with the literature, we will start from the 1989 till date, and this literature is still evolving. Okay. So the improvements in the CNN architectures can be categorized as parameter optimization, like filter size optimization, how we were constructing this feature map, those size optimizations, and structural reformulation. That is very important, and you will see these in each and every step. Okay. The main thrust of CNN performance improvement came from the restructuring, that's what I was telling, of processing units and the designing of new blocks. Okay. We will see this point of focus step by step. Let's first start with this spatial exploitation. What we mean by spatial exploitation? That means CNN has large number of parameters and hyperparameters. Okay. That means we talked about weight. Yes. Any questions? Yes. Tell me. Yes.
I think so. Means the slides are not visible.
Huh?
Yeah. Yes.
What?
Now it's visible, ma'am.
Is it visible? Oh, sorry. You. Okay. Visible, right? Okay. So we were talking that the CNN, this literature started from 1989 till date. Until that, it is evolving, it is improving, and that improvement is basically restructuring some blocks and reorganizing some blocks. Now, first take this example, that is LeanNet. LeanNet was the first CNN architecture. So, from LeanNet, this concept, the spatial exploitation, what we are pointing to, it came into figure and it became the state of the art, which that was first applied on this digit recognition task. It first shown this concept of convolution, applying this filter and getting that output, then what is the purpose of pooling, and then it actually basically formed the initial first CNN structure along with some 5 alternative structures, layers of convolution and pooling, and then 2 fully connected layers. In every case, you will see that some fully connected layers will come at the end. So that was the basic structure of LeanNet. And it was first used for digit recognition task, exploited the underlying basis of image, that the neighboring pixels that correlated to each other and feature motifs are distributed across the entire image. This part is very important. That means this concept that if you apply this type of filter and certain size of filter, you can extract some pattern. That means neighboring pixels, they have some correlation to actually form that image or subpattern within the whole image. That was first observed in this linear. That is giving the first concept of this linear. Okay. Therefore, convolution with learnable parameters is an effective way to extract similar features at multiple locations with few parameters. So that way, this type of alternative layers of convolution, pooling, and fully connected layers, with that LeNet first came into picture. But what was the problem of LeNet? LeNet was only considered like one input pixel. Each pixel was considered as a separate input feature. That means now what we are telling? We are telling that in general, when we form this neural network structure, we consider the features as the input, as the components of your input layer, right? This is your input layer, the components you are considering, those are one your features. But initial concept was not the same. LeNet considered these are all the input pixels. Okay. If that is so, now you of course can understand. After that, LeNet was doing this convolution. After that, it was doing pooling, etc., etc. It was with and it all done on top of a huge input layer. Okay, and also that time, actually, whenever one subject improves, that gets the support from other supporting improvements. And this machine learning, the evaluation of machine learning, improvement of machine learning architecture came into picture and was prominent also with the support of GPU. Okay. How GPU type of platform, the implementation platform different from your normal CPU? Here you can get in GPU, you get maybe those who have never worked on GPU and have no idea about what is the base. Why do we consider GPU for this machine learning purpose and for this type of operations? Now you observe in general what you are doing in your machine learning. This fully connected layer or maybe in convolution layer, whatever it may be, you are basically doing some matrix multiplication. So that means repetitive same type of operations you are doing throughout your input feature map. So what is the requirement? How you can improve in terms of computation time? If you can execute all these multiplications in parallel. Okay. That means once you are this filter is applied to this part, and once this filter is applied to this part, all the results will be computed in parallel and you will get the output. If that can be done, of course, this computation time will decrease. It will be faster. So in that way, initially when LeNet was proposed, this concept was not there. GPU was not in picture. Only CPU was there, and here you have to go for serial processing. You have to do first one multiplication, then you have to, that will complete, then you have to come for the next multiplication. That way, when GPU came into picture, the scenario it changed a lot. Why? Here the concept is, let's say this is your kernel. Kernel means you have considered some core operations. Like here, maybe you are multiplying the filter with some input feature map. That is your core operation. Now you are breaking those core operations into the sub operation, and you are offloading them into some blocks. That means whatever you are doing with one filter, next, after applying some stride, the new locations you have considered and the filter, the next multiplication, you have basically mapped to the block number 2, block number 3. That way, all the multiplications you have ported to different blocks of GPU, because the main concept of GPU is it is having some smaller processing units that can support parallel process. Even within the block, you can have threads. Now you think about the multiplication. You have this, maybe, and this. One is coming from your input feature map, and one is coming from your filter. What you are doing? You are repeatedly doing multiplication with this, and so on. Now, this initially in CPU case, you had to wait. You waited first, you will finish this multiplication, then only you can go to this next small multiplication. But now when you are having GPU, basically you are offloading this multiplication here, this multiplication here, and so on. So that way, with the invention of GPU structure, GPU architecture, that helped machine learning a lot to improve in terms of performance and decrease in terms of computation time. Okay, is that part clear? But when LeNet was first proposed, that time this GPU concept was not there, and also its input layer formed with all the pixels. That's why LeNet was only successful for this hand-digit recognition, where number of this type of pixels, those are very less. But it was not suitable for huge complex images or complex, this feature learning technique. Okay, is this clear? Any question? Anyone? Can you hear me? Hello?
Yes, ma'am, you are audible.
Okay. So this is the basic architecture and this is the limitation of LeNet. From there came the AlexNet. Okay. So what AlexNet did? AlexNet basically extended this layer from 5 to 8 layers. Okay. So that is one extension, and with that extension, and that was also supported by GPU, etc. Because when AlexNet came, then GPU concept was already. So in that way, it was possible to improve the computing time. It was possible to make things parallel, and it was possible to support more layers. Okay. And what was the concept? That depth improved the generalization. Okay. Depth in layer increases means you are increasing more number of related filters. You are increasing more number of features, and you are actually capable of identifying more in-depth features, more high-level features. Okay. But one thing is that, yes, depth, it is the advantage of AlexNet, and it is also the disadvantage of AlexNet. And there comes the concept of this overfitting. This is not, overfitting was one, some old concept in machine learning, but it was people again observed this kind of overfitting concept in AlexNet. What do we mean by overfitting? Let's give one simple example. Okay. Let's say for this course, you are skipping the class, you are not listening anything. And since your video off, you are muted, so I also do not understand whether listening you are following the class or not. Okay. At the exam time, you have just marked up the slide, and if I am giving, now there are two things may happen. If I am giving you questions, exactly whatever mentioned based on whatever mentioned in the slide, exactly term by term, word by word, you have marked up so well, you are performing 100%. Okay, that means you have trained with the slides so well that based on exactly same training input, your accuracy is 100%. Let's think in this way. Okay, but now if I am just tweaking the question a bit, okay, whatever there in the slide, maybe some problem formulation, or I'm tweaking the question a bit. That time you have actually marked up the line by line, but without understanding proper meaning of the all the input features or meaning all of the, I mean the training is, what to say, it is too much followed by the features, and maybe some extra features have been considered that it may have, that maybe some noise, maybe some wrong variations present in the slide. That means you will also follow that wrong variations, wrong information present in the slide, and you will write your answer accordingly. Okay. Now, in case of test data, maybe your test problem, that may go wrong. That means in this case, when we are talking about training accuracy, that means I have trained on some data and I'm again trying to test with the same trained data. My accuracy is very high. Okay. But when I am training with some, I am testing with some other test data, that time I can see significant percentage of error. Okay. Now with this example, you map your bias and variance with this training error and various variance with this testing error. Okay. Now in some scenarios, it may happen that whatever training is done, it has not considered proper features, it has not considered all the features, and somehow this training error is also high. That means you can map this bias with this training error, and at that time you have high training error, or you can say that is high bias. Okay. And if training is not proper expected, that you will get significant amount of error in testing phase also. So that we are mapping this variance with our testing error, and that time we will have high variance also. Now, when we have this high bias and high variance both, this scenario is called underfitting. Okay. This high bias and high variance both are called together underfitting. Now, this is very easy to detect. Underfitting is very easy to detect because whenever you see that in your training phase, when you are training and you see that your training accuracy is low, of course, what you will do, you will adjust the weight parameters, how we can adjust, etc. We will see that next day. As of now, you just think that you have some option, you have some way out to adjust the weight. We will adjust the weight, and based on that, you will try to reduce that training error. Correct? That means you are reducing your high bias and you are trying to make it as low bias. Okay. And after while doing this, once bias is low, at some stage you have seen, okay, for your test data also, test error is percentage of test error is low. That means that is from high variance you are coming to low variance too. But next you are considering, after this you are considering some more features from your training input, and maybe that time this training input along with this training exact features, maybe some noise has also been considered, and with those noise and the training input features both are considered during your training phase. That means fluctuations in the training phase, noise incorporated in the training phase, everything has been considered in during your training phase. What will happen now again, if you, since this noise, these fluctuations, those are the part of your training set, training data. So when you try to test your training accuracy with your training data, of course you will get low bias because those noise, those fluctuations are the inherent part of that training set. So you will get low bias. But this time, what I was telling that this time, if I give exact questions from the slide, whatever mistakes there in whatever mistakes already there in the slide, also considering them, then you will do perfectly well, no problem. But if some variance of the question comes, or if the test data is slightly different and it is not incorporating similar type of noise, then your test error will be high that time. That means this is called the high variance. And this scenario, when your training accuracy is high, that means you have low bias, but your training test accuracy is low, that means you have high test error. This situation we term as overfitting. Okay, is it clear? What we understand by bias and variance, and especially what we understand by overfitting, because this term we are going to use repeatedly. Overfitting means, yeah. Any question? Okay. So that means in case of overfitting, when you are, so why we are talking this in the context of AlexNet? Because when you are considering some improved depth, you are increasing the layers, you are extending them to 5 to 8. In some cases, this type of input training set noises, some disturbances, also taken into account, but not isolated properly during the training phases. And that may hamper your test accuracy. That's why these drawback, whenever you are increasing these layers, this drawback, that means increasing is the training inputs, increasing the depth in the training phase, that time this drawback may be associated that with the increase of depth, this overfitting may be observed. Okay, so this is one limitation of this overfitting. Another will be coming from the back propagation part, that is during the training phase, there is a vanishing variant. Maybe that we will discuss next day, and we will see what are the solutions and what are from there how other types of this type of NN architectures are evolving, proposing like LSTM, hybrid networks. So they are coming to bypass some parts to avoid that type of vanishing variant problem. Okay, that we will take maybe next day. Is there any question? Is it clear, this part? Or should
Yes,
I
ma'am.
repeat it once again? Okay.
Hello,
Hello, yes.
ma'am. This part is clear, but ma'am, when before applying activation function, some bias is added. So,
Yes.
what is that significance of that bias in CNN context?
Okay. See, in general, when you are adding bias, why you are adding bias? It may happen, right? One second. See, here also we have added this bias. Yes. Here also we have, before activation, we have added some bias. Okay. In general, maybe you are getting some models like this. This type of models. Okay. Where this your actually this models it is going through this your exact axis, this 001. But actually it may happen in your real scenario. Maybe next day I will come up with an example, then only you can better understand what is importance of this bias. So this shift is necessary. That means the real model where your that is getting mapped, the model that is getting mapped to the real life example or real problem, that is not having that is not supporting these kind of root values. Okay, so then some shift is necessary. So this bias is basically for that shift. Maybe I will come up with, since you asked this question, I will come up with an example and I will explain it better. Okay, but whenever we need this shift, this bias is basically promising this shift. Okay.
Okay.
Okay. Anything else?
Ma'am, what are some techniques to reduce overfitting? What are the common techniques instead of except for regularization?
We will talk about that. We
Okay.
will talk about next day. We will talk about. We have just talked here about the overfitting. We will talk about this, the solutions of overfitting, along with that solution of that first that other problem of AlexNet, that is a vanishing variant problem, and what are the solutions. Okay.
Okay, ma'am.
Any other questions? If there no other question, then we may wind up for the day. So next day we will talk about that highway network and those solutions again. Okay.
Ma'am, will you be sharing the slides?
Yes, I have already shared. I think you have you checked that drive folder? The slides and there's recorded lectures. Everything those are shared. I think. Just check and let me know, okay, whether you can see it or not. Otherwise, I will change the access permission maybe.
Sure.
Okay. Okay. Thank you then. Bye.